Morning, dear students. Today we will talk about plane stress problem. Okay, for which we will try to derive the stress-strain relationship, and the end result is that we get the D matrix. Okay, so what we call D matrix is elasticity matrix or constitutive matrix. Okay, so this is what is our job. Right, what is a plane stress condition? Okay, so the plane stress condition says the stress components related to the dimension perpendicular to the plane of the body are zero. Okay, so for example, let the body is in XY plane. Okay, so plane stress condition for this body says the Z components of stresses like a normal stress in Z direction, shear in Z direction. Okay, so this is what this plane stress condition says. So let us apply this condition to the generalized stress strain relation that we have derived. So you know epsilon x is equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. Okay, this is the strain in x direction due to stresses in x, y, z directions. Similarly, we write for y direction sigma y by E minus nu sigma x by E nu sigma z by E. Similarly, epsilon z sigma z by E minus nu sigma x by E minus nu sigma y by E. Now substitute the plane stress condition, that is this condition, into these equations. Okay, so substitute plane stress condition. Okay, so now epsilon x will become sigma x by E minus nu sigma y by E. Sigma z is 0. Okay, epsilon y sigma y by E nu sigma x by E sigma z is 0. Okay, similarly strain in z direction sigma z is 0, so first term 0, second term and third term will remain. Okay, yeah, so now we need to derive the stress strain relation. Okay, this is strain to the left hand side and stress components to the right hand side. So let us consider the first two equations. Okay, because we need expression for sigma x, expression for sigma y. Okay, so let us eliminate let us eliminate sigma y from the first two equations. Okay, so to do that, you see, first term I have nu multiplied by sigma y by e. Second term just sigma y by e. So I need to multiply the second equation, multiply epsilon y equation with the new. Okay, so if you do that, see, I get nu epsilon y is equal to nu sigma y by e minus, there is already nu here, so it will be nu square sigma x by e. Okay, so now let us write the epsilon x, the equation 1. So sigma x by, I'll write this first, like minus nu sigma y by e plus sigma x by e. I just rearrange these two terms like this. Okay. Yeah. Now just add those two equations. Okay. So what we get? So adding these two equations. So left hand side, you see nu epsilon y plus epsilon x, left hand side. Right hand side, you see the first term is common here, and then if you take sigma x by e common here, okay, it is 1 minus nu square. Okay, now just send the terms to the other side. We have sigma x is equal to this. Here it is 1 minus nu square by e. So when it comes to the other side, e by 1 minus nu square into epsilon x plus nu epsilon y. Okay, so this is a sigma x equation in terms of strains and material property. Similarly, you can carry on with the sigma y is equal to, okay, e by 1 minus mu square, okay, nu epsilon x plus epsilon y you get. Okay, so this is what you get. Okay, so this is sigma x and sigma y expression. So to get the shear relation, so we use direct relation. Shear stress of xy is equal to shear modulus into shear strain. Okay. Yeah, to replace G from the fundamental relation, E is equal to 2G into 1 plus mu. So where I need a G value, so E divided by 2 into 1 plus mu is equal to G. So substitute this into this equation. So I'll get tau x y is equal to E by 2 into 1 plus mu gamma xy. Okay. So now this is the stress strain relation for plane stress problem. Now to get the D matrix, where the D matrix is nothing but the relation sigma is equal to D into strain. Okay. So now we have for plane stress case, This is the left hand side matrix, and we need to find this D matrix. So we have epsilon x, epsilon y, and gamma x. So now we need to arrange these three relations, sigma x, sigma y, and tau xy, into this matrix form. That's it. Okay. So to do that, see, we have these two equations. We have a common term of e by 1 minus nu square. So the same thing, if I have it for this also, like for shear relation also, then we can take that as common term, that e by 1 minus nu square. So how to put e by 1 minus nu square common term? So to rearrange this tau xy, e by 1 minus 1 plus nu into gamma xy. So I need 1 minus nu square term. So I'll multiply with 1 minus nu by 1 minus nu, okay, divide it by 1 minus nu, right? So now if you multiply this 1 plus nu and 1 minus nu, what you get is 1 minus nu square. So e 1 minus nu gamma xy divided by 2 into 1 minus nu square. So this is our common term. Okay. So which means e by 1 minus nu square is the common term. So what is remaining is gamma xy into 1 minus nu by 2. Okay. So this is the tau xy equation ready for the common term to take out. Okay. So let it be. Now I'll write the matrix form like sigma x, sigma y, tau xy. So the common term is e by 1 minus nu square. So now the matrix form, then epsilon x, y, gamma x. Okay. Right. If you see the first equation, so this is common. So 1 into epsilon x plus nu into epsilon y. Okay. So 1 nu, the shear term is not there, so 0. The second equation is nu into epsilon x plus 1 into epsilon y. Nu 1 0, no shear term. Yeah, this last one, this is common. Okay, epsilon x 0, epsilon y 0, gamma xy, this is common term, and remaining is 1 minus mu by 2. So this is what is called the D matrix or elasticity matrix or constitutive matrix. Okay, so this is how we derive the stress strain relations for two-dimensional case. Okay, as well as the elasticity matrix to formulate it. Okay, right. Thank you. We'll see you in the next session.